With this, I like to welcome you back to my lecture Mechanical Properties of Materials, course number 315008. This is the spring semester 2022. I'm Klaus-Dieter. You know me already. We are now in the chapter of dislocation theory. I like to resume very briefly what I said last time. I talked about the Labarro-Peierls stress and then come more into the characterization of dislocations, the observation of dislocations. Right, last time I've introduced a width of a dislocation. So the width of a dislocation given by the parameter W is where we have this registry between minus Burger's vector force to plus Burger's vector force. So basically an interval of half the displacement. The full displacement would be 1 Burger's vector, which we put from minus 0.5 here to plus 0.5, and the half width of this is the half value of this is from minus half of 0.5 to minus half of minus 0.5. So this gives the values minus b force to plus b force. And then the distribution is the width W, which we have introduced. And then we can have narrow dislocations, and we can have wide dislocations. You see, in the narrow dislocations, if here's the dislocation, I go 4 lattice planes away, I'm almost straight already. While in the wide dislocation, I go also 4 lattice parameters away, or 4 Burger's vectors away, but I still see the inclination of the lattice plane, and it takes more distance until we see the vertical undistorted line. So that's how you can visualize it, a wide and a narrow dislocation. Because this is important when we switch the bonds. You know, when we move a dislocation from the position x0 here along this glide plane, along the horizontal position, then we have to switch this link to that link, that one bond to the next bond. And now it depends how easy or difficult it is to switch the bond. Because in the situation of the wide dislocation, we have already many inclined bonds. So if I switch from the inclination to the right to the left, there's not so much distortion in the symmetry between left and right. But then the dislocation would have moved 1 lattice parameter, 1 Burger's vector to the right. So this costs little energy, while if I switch, let's say, from here in the narrow dislocation from the right to the left, then I see I have to advance all the other inclinations by the Burger's vector at the same time. Or it is a large impact, because this inclination and that inclination, they are pretty similar. However, the left one should be straighter. So I have to put more energy barrier into the crystal to overcome this switching of position of dislocation. And this is expressed in this exponential function here. So the critical shear stress is the shear modulus times an exponential function of W over B. So W is the width of the dislocation, which is wide here, and which is narrow to the right. Well, always scale to the Burgers vector, and there's a factor of 2 pi. So it's an exponential decreasing function. If W becomes large, the energy barrier to overcome the switching is low, and therefore we only need a lower shear stress, tau c. Remember, in the perfect lattice, we got this formula. The modeled shear stress, if we displace the top lattice planes all stiff with respect to the bottom lattice planes, then we got something like G over 2 pi. There were some approximations, but it's not so bad. G over 2 pi. If we put now everything in, that the width is somehow related to the Poisson ratio, then it can be shown that we end up with this formula. Tau c is the exponential of minus 2 pi, and then we have that A over B again, and the 1 minus nu in the denominator. So this is an important formula because qualitatively it shows as the dislocation becomes wider, the applied or the critical shear stress I need to propagate the dislocation is smaller. Perfect. Well, if we talk about perfect, back to the perfect lattice, the width of the dislocation would be 0, and therefore we get a very high shear stress. Of course, the formula is not exactly the same in the two approximations. Right, then I introduced the observation of dislocations. So I introduced edging pits at the surface. You can edge the surface and get these pits. These are observation of dislocation loops by electron microscopy. Also dislocation in metals and silicon, in ceramics, so aluminum oxide, alumina, sorry, and titanium carbide. Any questions? No, I heard something. I have shown the observation of dislocation loops at these examples, so they exist. Dislocation arrays such as pile up here in the lines, and we will talk more about pile up of dislocations in lines theoretically later on. So here's a nice observation. Modeling of dislocations in this case in copper, so computer modeling during indentation or tensor loading. Tensor loading in this case. Here's an indentation, so we have an indenter, this hard red shaped tool pushing into a surface, and measure. You can measure the hardness, you can measure local strain stress curves nowadays if you have a certain shape of the indenter, because you also get some plastic deformation. Usually you push until you get plastic deformation. You push a hole into the surface, and that exposes a lot of dislocations into the material. Again, we have two types of pure dislocations. We have the pure screw dislocation, we have the pure edge dislocation, and then we have a superposition of the two, which is the mixed dislocation. So here again you see how they propagate and how they shear the materials by the Burgers vector B. Now let's come to diffraction. Observation by diffraction. So it can be electron transmission, microscopy diffraction. Or the same is valid for X-ray diffraction. And it would be also valid for neutron diffraction, but typically with neutrons you don't have the resolution, the spatial resolution to make the image. But dislocations, they change contrasts in diffraction. For example, if we have a crystal like this, with the dislocations there in the center, and you come in with a transmission electron microscope, then you may get some of the beam deviated. So first of all, you see you have an inclination to the lattice plane, so you get subbrake diffracted beam. Actually, here it's shown the other way around. You get subbrake reflected beam in this direction. It's only schematic. And if we look to the transmitted beam here, then we get a contrast which is something like that. It's constant, and around the dislocation we get maybe less intensity. And this is because the dislocation scatters intensity somewhere else. So we get a deficit of intensity. If we look to the brake diffracted beam, this is the scattered intensity. Then, as a function of position again, eventually the dislocation scatters a little more and we get a bump of intensity. So here we have the situation that the scattering vector and the Burgers vector, they are parallel to each other, or almost parallel to each other. So they are a large number, close to the maximum. It's a little tilt here. I would make the figure better. If we turn around the crystal so that we have the scattering vector G here and the Burgers vector perpendicular, as shown here in the extra plane inserted in the middle of the crystal, then in the bright field we don't get any contrast. So we don't get this dip which we observed here on the right hand side in the situation where we have the two vectors parallel to each other. G dot B is maximum. And also in the bright field there would be other lattice planes here in this direction, and that would give another bright field, and this bright field you would just have a constant intensity as well. So let me talk more about this G dot U rule. Here we have the product G dot B becomes maximal, and here we have a reciprocal lattice vector G, and we have the Burgers vector B. So B is the Burgers vector, but more generally it's the displacement field U which plays a role. So it's the displacement U of X, Y and Z, yeah? Y, Z. So it's a displacement U as a function of position, while B for dislocation, it is the displacement of the dislocation, but it's not a description of each atom at the position. Here the atoms near to the dislocations, they have, we can say here's a Burgers vector B, which is the overall, the integral of the U. So if you integrate all displacements over the volume around the dislocation, then you should get the Burgers vector B. So let's talk about U. And I put U of X just here in the horizontal direction, along the X direction, for simplicity. For each atom, We only have a u of x, we don't have a dependence in the vertical dimension in this model. So then, the situation we have with the dislocation is, we have a scattering vector g1, and we see, as we have displacements here, horizontally, eventually, some atoms, or the atoms, they move around horizontally in this direction. Giving rise to lattice parameters, if this is the equilibrium lattice parameter far away the dislocation, and here also, these are equilibrium lattice spacings far away from the dislocation. Then close to the dislocation, I have here a larger spacing. And here also a little different spacing than the equilibrium far away spacing. And here I have a very big spacing. You can see, and there I have a narrower spacing. So if g dot u is not 0, then I can see the change of the local change of lattice plane spacings. In contrast, if u is still horizontal here, and I put the lattice planes as the yellow planes here, with a g as g2, means g2 times u is 0, g1, g2, g times u equals 0, then I would not recognize, I don't see a change of spacing. So for these yellow planes there, the spacing is everywhere the same. The vertical spacing is everywhere the same. So I do not see the change of spacing, and therefore I don't get the contrast. So I only see displacements perpendicular to the lattice plane which contribute to new local lattice spacings, and that gives me a contrast. It adds or removes intensity depending on the situation I'm looking. So this is very general in diffraction. If you have distortions in diffraction, always look to the g times u. It's not g1, it's just g times u, any g. If it's 0, then you don't see it. And if it's different from 0, and if it's large, of course, you have a high chance to see it. If the g and u are parallel, then they get the maximum dot product. And then, of course, you have to get the maximum contrast. This is what is shown here. In the example by my friend Alain Courret from France. He also works on titanium aluminides, and that's how we know each other. And he looked to dislocations at 1123 Kelvin in this case. And he looks to the motion of dislocations. But also, what is interesting here is several pictures he took from the same situation of the crystal, but with different, in dark field, with different scattering vector orientations. So they're all 111 type. And titanium aluminide, this is almost cubic, it's a little tetragonal. So let's say it's almost cubic, so the 111 planes, they are approximately all the same for this consideration. It's not true, it's tetragonal, but there's orientation dependence. But let's say they're all the same. Then we see that there is change of contrast depending whether the scattering vector is in this direction or in this direction or even in that direction. That means if we look to contributions perpendicular to the scattering vectors, we would not see them. So where is this the case? There are few cases pointed out here to the right where we have a similar situations. We have the 2, 2, 0 direction, we have the 0, 2, 0 direction, and we have the 2, minus 2, 0 direction. It's not the same family of plane, but it doesn't matter. So we only want to look to the extinction if G dot U becomes 0. Then we don't see the contrast. And yeah, so we have scattering vector is here, and some dislocation which we see here is missing in the first picture. And here at the very bottom, so you see the same loop every time, yeah? Here's the same loop, here's the same loop, and here's the same loop of dislocation, or part of a loop. So I erase the ink. You recognize the loop in the 3 pictures, in the 3 images. And the dotted regions around there, these dotted lines, these dotted ellipses, this is where the dislocation is extinct because of the orientation of the scattering vector. So if the scattering vector is like indicated in this direction, if it's indicated in this direction, then we know the Burgers vector must be perpendicular to it in this direction for this dislocation here. Or at least the displacement, not the Burgers vector. Displacement has to be in this direction. And we see under different orientations, there are different extinctions. So here's this dark bar, part of the dislocation, which is extinct here. And as the scattering vector is like this, we see there's this part, there's this part here, which is extinct, which can be seen here and which can be seen there. So here again, it is explained in that subfigure. The B dot U is perpendicular to G, or B or U is perpendicular to G, and it is out of contrast. And when it has an angle to the scattering vector, then it is in contrast. So this is contrast variation by orientation of the scattering vector, and you can learn something about the displacement U, the local displacement U. If you integrate it, you get the Burgers vector. Schematically, this is shown here as well. Let's say we have edge dislocations and we do TEM. In the bright field case, we have the situation to the right here. So this is reciprocal space, and you select one of the beams. In the bright field, you select the transmitted beam, which is the 0, 0, 0 reflection. And you see dislocations. Let's say you see horizontal dislocation lines, those, and you see vertical dislocation lines. Because each of them scatters out some intensity into some of the other reflections. So you get a shadow, you get a shade of those dislocations in the bright field. Now if you go to the dark field and you select this reflection as shown here to the top, that means the scattering vector is vertical, and also we say these are edge dislocations, so the B vector and the displacement is mostly perpendicular to the dislocation line. Then we get contrast for those dislocations, but the other dislocation here, they would have the B horizontal, so B horizontal dot this scattering vector vertical up becomes 0, and that's why we don't see the other dislocation lines. The same if you choose the scattering vector here to the left, of course, then you see the B and the displacement U's, which go to the left or to the right, and you get contrast for those, while you don't see the dislocation lines where the displacement is up or down. So at edge dislocations, it's pretty much the Burgers vector. So I'm not a specialist in electron microscopy, but here's also a 2-beam bright field. So a 2-beam bright field means you get equal intensity in one of the reflections and in the other, and of course in the transmitted beam. Transmitted beam and reflected beam to the left, they have equal intensity. So what happens then? Let's try to solve this puzzle. If I get a lot of intensity scattered into this beam, then the intensity is not scattered vertically, it's not scattered to the small dots here of reciprocal space, it's just competing between the two, and that means I have basically a probe for scattering vectors in the horizontal orientation, and only see Burgers vectors again in the horizontal orientation and not Burgers vector in the vertical. And the same if you rotate the thing by 90 degrees. So two strong beam, you have the main beam and the break reflected beam. That means the break reflected beam goes onto the Ewald sphere. You have a 2-beam case in diffraction theory, and all the other beams are negligible with respect to these two strong beams. So here are further examples. I've shown you the example with the titanium aluminide because I love titanium aluminide. I worked a lot on them. But here we have aluminium oxide. And also see the same image. You see the bump at the surface here. Here's the bump at the surface. So the same area, not the same image, the same area with different scattering vectors in dark field. So high resolution transmission electron microscopy. 4 indices, that means it's a hexagonal structure. And in the hexagonal structure you can have Burgers vector along C, you can have Burgers vectors along A and C, and you could have some along A as well. And if you work out now the extinction rules, the contrasts, then you can see sometimes we have these little arrows here pointing to the dislocation line to the left. We see here there's no dislocation line. There you see the dislocation line. So you can work out from different exposures with different orientation scattering vectors the orientation of the Burgers vector. That's what they do. We don't do it in detail here. Just resuming the observation methods. There's a high resolution transmission electron microscope. So this is now where we can see the atomic columns. So we see basically the atoms in the plane, yeah, in the projection of this 2D plane shown here. And we can see the lattice parameters shown there by the two arrows. A and B looks like a hexagonal pattern here, yeah, so it's a hexagonal structure. I assume it's the same sample as before. There's no text here. And one can find out now, but the question is there a dislocation or not? Sometimes if you remove all these markings and so, it's difficult to find the location of a dislocation, particularly when the width W is very large. When it's very large, then the dislocation is distributed over many, many atoms, and you have difficulties to localize it. So you do the same trick as I showed you last time. You have to count the number of lattice translation vectors in one dimension and in the other lattice dimensions. So let's do it. Let's start here, and we go 1, 2, 3, 4, 5, 6. So I mark that down 6 steps up, and then we go 1, 2, 3, 4, 5 steps over. So now we have to go -6 down. 1, 2, 3, 4, 5, 6. We are here, and we have to come -5 over. We go 1, 2, 3, 4, 5, and we end up there. So we are not ending up at the same position where we started. This is the difference, and the difference is the Burgers vector. If we go far away from the dislocation, it's exactly the Burgers vector. That means somewhere in this area here, including the Burgers vector, is a dislocation. Now it's really hard to say, is the dislocation, is it here or is it there? It's hard to say, but we know. And that really depends on the width W of the dislocation, whether it's hard to say or not so hard to say. But we know there is one in, and of course, if the dislocation is wide, then many unit cells are distorted. If the dislocation is narrow, less unit cells are distorted, but of course they are stronger distorted. So that's the difference. But importantly, going around, you end up at a different location, means there is a dislocation inside this loop. So that's another observation, and how to evaluate the pattern. Another nice technique is the large angle convergent beam electron diffraction method. So large angle convergent beam electron diffraction. We have to digest this. Did you hear about that? Anyone? Still there? No one heard about it. Okay. I'll tell you one thing, I didn't hear about it until I gave the course the first time. But since I do diffraction, I do X-ray diffraction, I do neutron diffraction, dynamical theory of diffraction, and that's all very, very related to electron diffraction. It's the same thing. So, easy to understand from my part. Tricky for a newcomer. So we have to digest this. It is diffraction. Diffraction means Bragg diffraction, lower Bragg diffraction. Bragg's law, lower equation. It's electron diffraction because we do electron microscopy. It's large angle diffraction, so it's not small angle diffraction. It's typical normal angle lower Bragg diffraction, lower Bragg interference. Yeah, Bragg's law. You have learned Bragg's law. So that's relatively large angles. But here we have a convergent beam. So this is the tricky part, the convergent beam. When you do X-ray diffraction, you have a sharp beam, and you measure one angle sharply and measure where the peak is. Here we have a convergent beam and we take an image. So I found this in literature here by Moniroli et al. There's a link and there's the picture. So if you have a sharp beam like X-ray diffraction, we come in with a well-defined beam. We have a lattice plane and get reflected there, and this is a scattering vector G. Now, if we have a divergent beam means we have intensity in all that cone, or convergent beam, a focused beam, yeah? So it comes in many beams like this, beam parts, ray traces like this. They come in and they converge to a point. So that means this same lattice plane, this same scattering vector can be fulfilled if we have a beam coming a little from the back and going here a little to the front. So I have a component in this x direction, if I call it like this, and having the same scattering vector. So that means if I now look to the beam orientations all coming in with the same in-plane angle but with different orientation, then I get a straight line in reciprocal space which is perpendicular to the scattering vector, which fulfills one after the other the reflection conditions. And there's the assumption that they have a certain energy spread, a certain wavelength distribution or k-vector distribution in the length of the incoming wave vectors. Okay, so I get these lines. Instead of a spot in reciprocal space, I get a line in reciprocal space. I get this line of reflected beam, and then I can do some optics. So I go through the focus, and in the back focal plane I may get an image again, and I get, if I look to the transmission image, which I see here, then I can map these lines. And these lines are deficiency lines because the intensity is missing. Along these lines, intensity is missing because it is reflected here. It's reflected to this position. So it makes this Bragg reflection, as I said, yeah, by the scattering vector there. So incoming, outgoing, it goes to this position, to the right. But there I have a hole, I have an aperture, so that I only look to intensity which goes through that hole. So the Bragg scattered intensity is missing. And that gives a deficiency line for that one scattering vector G or lattice plane family HKR, GHKR, or lattice plane family HKR. Then we know if we have HKR, we also can get minus HKR. There's another deficiency line. And we have other lattice planes. Typically in the crystal, we have lattice planes in other orientations. Then we would get other lines, more lines in the image, more deficiency lines due to other Bragg reflections in the image. So here we see these deficiency lines. We see there's intensity, and where there's a line, the black line here, it's dark. Dark means there's less intensity. So we see the line from HKR for H prime, K prime, L prime, and for another HKR family, for another HKR family. So for different HKRs you get the different lines. And we have the strong lines for lower index HKRs, and then we have the weaker lines for typically higher index HKRs. You know the structure factor plays a role in diffraction. The structure factor, if you go to higher Q, higher HKR, the lines become weaker, or the structure factor becomes weaker. Interestingly now, we see some areas in the line, like between these dotted lines, where we have a distortion of this horizontal line. This is the horizontal Bragg line. We see distortions, and we see fringes, interference fringes. This is schematically shown here. So I would start with a continuous line. This is what you have in a perfect crystal. You have these continuous lines. Now imagine there is a dislocation. Dislocation line is shown here by this little horizontal white arrow. And in the field, in the strain field of the dislocation line, first of all we see a bending. So the bending, the reorientation of the dislocation line is due to the reorientation of the lattice, the reorientation of the local lattice around the dislocation line. Yeah, you remember dislocation is something like that, where we have bent lattice planes. So around the dislocations they are a little reoriented, and this reorientation over Bragg diffraction magnifies to a large angle. Even if the angle is small, but with Bragg diffraction you can magnify this reorientation angle to a large amount. So this is the bending qualitatively. And then we see fringes. Yeah, we see white gaps or black gaps in between. Yeah. So the line is white in this contrast here, and then we see 1, 2, 3 black gaps. So for n equals -3 or for n equals +3. So here G times B is n. This is in the notation where G is 1 over D, or we have G equals 2 pi over lattice spacing D. Then we need to take this equation in brackets. So the n is then G dot B over 2 pi. Depending on the convention of the reciprocal space vector G, whether you have a 1 over D or 2 pi over D. Then, if it's 2 pi over D, you have to put the 2 pi in again. But this G dot B gives a fringe number n. And what it is, this is basically the Moiré fringes between the scattering vectors, or the lattice spacing, change of lattice spacings locally in the vicinity of the dislocation with respect to the average lattice far away from the dislocation. So you get Moiré fringes. You know what Moiré fringes is? You take two, maybe there's something on the internet, Moiré fringes. Here you see them, Moiré fringes. You have two inclined lattices, or two lattices with different frequencies. So here are some distortions, here some distortions in, you have a perfect lattice. You superimpose them, you get these fringes. These are called Moiré fringes. And you see there's some distortion, and the distortion field makes up these black and white areas depending how these lattices superimpose. Whether a dark line superimposes a dark line, then you see the white in between, or if the dark is on the white, yeah, then it looks all dark print here. And very similar, you see that also in crystal lattices, where you have a crystal lattice which is undistorted, and then you have that crystal lattice of this dislocation, just locally around the dislocation. And that gives rise of Moiré fringes, which are expressed like this. And mathematically, it can be shown that G dot B, that gives a number n. So, and that gives the number of minima in between these fringes. So this is a little excursion to electron diffraction and the theory of diffraction, including the dynamical theory of diffraction, which is behind this, which I may teach in the next semester. It's not decided yet. Right, so here time is running. Another slide on large angle convergent beam electron diffraction. If you want to know more, look up Morniroli et al. Maybe you can pronounce him better than I. You look to a dislocation line, you look to the width of the dislocation and the width of the dislocation and the orientation of the dislocation, and then the width plays a role, of course, in the area or in the width of the splitting here, and some optical and lattice gradients, they play a role for the bending. So you see some of them are sharply bent, others they are not so sharp bent. Some distribute more, some distribute not so far. As I said, these are Moiré fringes, and they represent very well the distortion of the local lattice. So we can work out, if we know G dot B is this integer n, or n over 2 pi times 2 pi, then we just can count here 1, 2, 3 minima for this direction, and we probably know some diffraction vector. So diffraction vector can be -1, 1, 3, and from this you can then work out the orientation B and the magnitude B. So this is a quantitative identification of Burgers vectors from large angle convergent beam electron diffraction patterns. A few minutes more and then I'm through this observation chapter. I've shown diffraction contrast with electrons. Of course, you can do the same with X-rays. X-rays that penetrate into the crystal, they get break reflected at the crystal planes. And if you do that with a large parallel, let's say a parallel incoming X-ray beam onto a wafer, a large surface. Then you also can look to the imaged beam, same as dark field imaging, the same you can do with the X-ray. So you come in with a large X-ray beam, you have a crystal here, yeah? And lattice planes like this, so they diffract like this, and the transmitted beam goes there. But now you put a detector here, put a film there or detector there in the diffracted beam, and that's dark field imaging. It's the same thing. However, in X-ray we call it topography, because topography is making a map of the crystal. Topography, you know, it's mapping when you draw a map of the world. And here we draw a map of the crystal. So we are position sensitive. And you can see here's a crystal. What is it? I guess some semiconductor. And on the edge there are some dislocations near the surface of the wafer. So this is a wafer which has a few centimeter diameter, 5 or 10 centimeter diameter. And near the surface something has happened, maybe during the crystal growth or so. And we can see the dislocations. And then also by reorienting the scattering vector into different orientations, so these are orientation angles, we get the same contrast factor G dot B or G dot U. And then can work out the dislocation. So sometimes you only see these dislocations, sometimes you only see the horizontal dislocation lines, and sometimes under some 45-degree angle we see them both. From that you can work out the orientations and also the Burgers vector from the extinction rules. Same as electron microscopy. And last not least, here's a movie where material, I think silicon, yeah, silicon is heated up before melting at T0. So that says before T0 there in the legend. So it does melt at T0, and you see there's a lot of dislocation movement. You see these slight shades moving from one side to the other side, and this is because when you hold a crystal, typically when you hold a crystal it's never stress-free, and even if you put it on a table, but atomistically it's never stress-free. So you have stresses, residual stresses from the suspension or whatever, and the material becomes so soft before it melts that it deforms plastically under its own weight, and you see the movement of dislocations. This is very nice demonstration, literature references shown there to the bottom. This is what you can do with synchrotron radiation. Okay, I think that's it for today. Time is over. You must be tired. And I have introduced now what are dislocations, how can we observe dislocations, and next week I like to introduce the plastic deformation of single crystals by slip as shown here. So that's how we go quantitatively into the orientation and plastic deformation of crystals. Thank you very much. And if you have a question now, I don't know how to stop the sharing. The panel is gone.
Yes, Professor.
Yes?
I want to ask about whether the Burgers vector, just like the direct lattice vector.
The Burgers vector is one lattice vector. We have many in the lattice, in the crystal lattice, we have many lattice vectors, many translation invariant vectors, and the Burgers vector is one. The Burgers vector is one, which makes up the displacement when you go far away. So the additional plane you put in. You put an additional plane into the crystal, half plane, and there's a discrepancy, this registry. If you go far away on the plane below and on the plane above, then on the plane above you count one unit more than on the bottom, and that's called the Burgers vector. Or as we go around in a loop, you remember we went around in a loop, and that would give you the Burgers vector. So let's say we have the dislocation here, and here we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So here we have 5, so something like that, yeah? Now I count here 1, 2, 3, 4. And here are 1, 2, 3, 4, 5. So the top lattice, top half lattice has 1 unit more than the bottom. And this difference we call a Burgers vector. And we can see that when we go around in larger loops. So if we go a loop around here and we not end up at the same point where we started, let's say we started there, we end up at the arrowhead, then this displacement is called the Burgers vector. Is this your question?
Yes, I got it.
Right. Well, of course, locally there may be smaller displacements in the Burgers vector. So if you go far away, the result is one Burgers vector. If you go close, then you have a strain field which is locally x, y, z dependent in general. If there's no question, tomorrow we have office hour. I invite you there. Please come and have a good evening. I will now kill this thing because I'm not sure how to get out of the Zoom. Yeah, end meeting for all. Okay, I leave you here. Bye.